In this video, I'm going to go through our next section of conics, which is section 8.2, and this conic that we're going to talk about is the ellipse. I think we already have a pretty good idea of what the graph of an ellipse looks like. We know it's related to the circle. It's not a perfect circle. It's just got that ovalish look to it. Probably aren't as familiar with the mathematical definition of an ellipse, so I'm going to show you that. It is a little lengthy. It does have some new vocab and things like that in it, so we'll try to pick apart that in this video just to try to help you have a better understanding. So I know, don't freak out. Again, you can kind of write what you feel like you need to get the idea. But as far as our definition goes, we're talking about an ellipse being the set of all points whose distances from two fixed points have a constant sum. These two fixed points are what we want to talk about here for a minute to try and give you a visual of the ellipse. The fixed points are called the foci, which is the plural of focus. So we talked about focus with the parabola, and so that was that one key point off of the vertex and inside of the parabola. With an ellipse, we have two of these key points, and they also are going to be inside of the ellipse, and they're going to be measured off of the vertex. And actually, we're going to have two vertices, so that's where we're going to see those. If we draw a line through our foci, that's called our focal axis. Right in the middle of all of that is what we would call our center. And where the axis and the vertices intersect, oh, that's just giving you the vertices. Okay, sorry, got a little mixed up on the words there. All right, so if you need to still copy some things down, I am going to switch slides to show you a picture, so just hit pause before I do that. Okay, so in the definition, they talked about the two fixed points, the foci, and that their distances, if you took the sum of their distances, so if you look at the red line and the blue line, that's the distances of the foci to a random point on the ellipse. Down here, this is showing their sum, so if I take the red plus the blue, that's their sum. Now it's saying this sum should not change no matter what the point is around this ellipse. So if I drag this point, if I move this point, while the blue and red change, notice the sum stays exactly the same. The sum never changes the distance from F all the way to G. So that is how an ellipse is created, off of these two fixed points and taking their, like wrapping it around, and that sum stays the same. So kind of a cool picture for you, just to give you an idea of where the foci are and what their importance is. All right, back to our notes. There is a lot of kind of verbiage and vocab that goes along with ellipses. While I think they're the easiest to picture and to create the picture for, there just can be some language barriers. So again, you've got a center. That should be pretty basic and easy. Notice I've got two different kinds of ellipses going on here. One that is longer, maybe think about a little wider than it is tall, and this one's a lot taller than it is wide. One side is always going to be longer in an ellipse. That's what makes it not a circle. And that longer side is what we call our focal axis. It's kind of like the major axis in the ellipse. So you'll see that that's different for each of these. And if you remember from the definition, the foci lie on this focal axis, and they're going to be at some fixed point. We'll talk about maybe more exactly where this point should be later, but there is a fixed point inside the ellipse on the focal axis. All right, so there's our foci. The vertices are also on the focal axis, and it's where the ellipse intersects the focal axis. So our vertices are here and here. And we talk about a major axis and a minor axis. Major is the focal, minor is our other one. So if you have a semi-major or a semi-minor, that's just half. So semi-major is basically from the center out to a vertice, and then semi-minor is going to be from the center Now, these points out here, they are still really important. They're not the major vertices. Sometimes people call them the co-vertices because they do really help us get the graph of an ellipse. We're going to want 4 key points to draw it. So I'm going to call these the co-vertices. And the semi-minor axis is just halfway between these, just from the center up. I labeled mainly everything over here, but you could get the same idea with the vocab on that ellipse. All right, so what I want to do next is just take a look at the standard form of an equation, which I think you should be familiar with. Just from when we did parametrics, we real briefly saw this idea. Key thing is these equations are always x squared and y squareds on tops. Then there's some number on the bottom that is representing a squared quantity, and it's always set equal to 1. So that's how you get your equation for an ellipse set up and know that it's in standard form. In both of these two basics, again, I just swapped the order of the fraction. It really doesn't matter. But they have centers at 0, 0. And one thing I didn't mention over here, I had this A, B, and C on the bottom. We call the distance from the center to the vertice our A distance. We call the distance from the center to our co-vertice the B distance, and then the distance from the center to the foci is our C distance. Now, how does that relate to the equation? Well, you're going to see, because I give you A squared and B squared, I'm going to be giving you the distance to the vertices and the co-vertice. Because A is representing the vertices on the major axis, or the focal axis, look at the variable it's under. It's under the x, which means in the x direction, my center's at 0, 0, in the x direction, I'm going to go out left and right, whatever my A happens to be. So that means my focal axis in a scenario like this is the x-axis. Oops, need to erase that. Okay. Over here, notice the A squared, and I didn't have to necessarily put the y squared first. I could have had the y squared second and still had the A squared underneath it. The A squared is going to be the bigger value, and it's going to go in the y direction this time. So this time we would go up and down with our A, and our focal axis would be the y-axis. The other standard form you guys have on your paper is when the center is not at 0, 0. So very similar to our circles and parabolas, this HK idea. Whatever's with x is the h, whatever's with y is the k, and that can give you your center. So the center can move, and then you will be going up and down off of the center and left and right off of the center with your distance to your vertice and your distance to your co-vertice. Just a quick example here. If I maybe make up like x minus 3 over, say, 25 plus, do a y plus 1 over 16 equals 1. If this is our equation, again, the A squared is that major axis, the one that's longer, so that's how I know that 25 is my A squared, and it's going in the x direction, but we're going this time off of an actual center that's not 0, 0, so I'm going to go over 3, down 1, 3, negative 1, and from here, I'm going to have to go left and right 5 units to get my vertices set up, so I'd go out 5, this way 5, I'm being real sketchy, and then here I'd go up 4, down 4, but this is my focal axis. This is that major axis because it's got the larger length, the bigger A value on it. So this would be the equation y equals k. So what would happen is if the A squared is underneath the y value, and we would be going up and down for our major axis, the focal axis would be the x equals equation, so x equals h. when you pick out this information, again, if you have a sketch in front of you, it makes it real easy, I think, to see what the equation for these focal axes would be based on what your bigger value happens to be under. All right, so we talked about A and B, and that helps us get the vertices and the co-vertices. But what we didn't talk about is how do we know where exactly to put the foci if those are some key important points of the ellipse. So I want to show you a relationship right now between A, B, and C. So we know that from the center to the main vertex is A. This is our A. And we know that from the center to the co-vertice is B. And this C distance is the distance from the center to the foci. So what I want to show you is that we could actually make a right triangle out of this distance C and this distance B, and then if we connect the two, we have this right triangle. And so we know with a right triangle, we could create a Pythagorean relationship. In this one, we would say b squared plus c squared equals this hypotenuse squared, coincidentally, always ends up representing this A length. So it's a Pythagorean relationship, but the variables are a little different than what you're used to, so you just have to be careful. This is the distance to the co-vertice, this is the distance to the foci, and this is the distance to the main vertice. So it's set up a little backwards. You're going to be given a squared and b squared in your equations, so it's typically the c that we're solving for. So realize c squared is equal to a squared minus b squared. Super important relationship to help you answer some questions and get some equations set up and know where to label things. So just be careful with it because it's not the same as you're used to, but we could see the same relationship over here as well. So this is important for a lot of our calculations. All right, I think that is going to be it for the intro, and I'll make a separate small graphing video.